Okay, so our topic is diagonalization. And what is diagonalization? First definition is diagonalizable matrix. First topic is diagonalizable matrix. A square matrix capital E is said to be diagonalizable matrix if if we can find non-singular matrix capital P, if we can find non-singular matrix capital P, so that P inverse AP is diagonal matrix So the thing is, when we want to prove that a matrix is diagonalizable, then it depends on some other matrix. So we want to find this matrix P for A, so that P inverse AP is a P inverse AP is a diagonal matrix. In this way, is a diagonal matrix. So now the thing is how we will find this P. Okay, this is for numericals. Remark. Remark says that when you have a matrix P, step 1, you find A minus lambda I determinant is equal to 0 implies you will have eigenvalues. Fine. When you have eigenvalues, for example, this A matrix is n cross n matrix. Okay, so you have n eigenvalues, lambda 1, lambda 2, up to so on lambda n need not be distinct. Now what happens is, step 2, you find eigenvectors. When you find eigenvectors, you will be having x1, x2, up to so on xn. You will be having these vectors. Using these vectors, you find x1, x2, up to so on xn. Okay, and this is your required matrix. P inverse AP will be diagonal, and it will be lambda 1, lambda 2, up to so on lambda n. Okay, now there is a caveat here. What I am trying to say is, for example, this is case 1. You have, for example, for understanding, we say that this is a 3 cross 3 matrix, and when I get eigenvalues, I get lambda 1, lambda 2, and lambda 3 all distinct. When I have all distinct eigenvalues, then this lambda 1 will be having its own linearly independent vector capital X, eigenvector capital X. Similarly, x2, similarly x3. So to multiply A with this P inverse and P, we need a matrix of order 3 cross 3. So P should be of x1, x2, x3, and it is a 3 cross 3 matrix. You can understand this thing, and when you multiply this, it will become diagonal lambda 1, lambda 2, and lambda 3. How it come? We will do in a theorem. Now case 2 is you have 3 cross 3 matrix. When you have a 3 cross 3 matrix, then I am saying that two eigenvalues are same, and lambda 2 is sorry. I am saying that two eigenvalues are same, lambda 1, lambda 2, and lambda 2. You have these three eigenvalues. One eigenvalue is repeating itself. You should understand that arithmetic algebraic multiplicity of lambda 1 is 1, and algebraic multiplicity of lambda 2 is 2. Now next step is, we will find eigenvectors. When you will find eigenvector corresponding to lambda 1, you will surely be getting x1. Now the most important thing is, there is a theorem which says geometric multiplicity will always be less than algebraic multiplicity. We know this eigenvalue lambda 1 has occurred only once, so geometric multiplicity of lambda 1 will be equal to 1. This means that the eigenvalue which is appearing only once will be giving one eigenvector for sure. The things are dependent on lambda 2 now. You have lambda 2. When you have lambda 2, you ask lambda 2. This lambda 2 is itself being eigenvalue for 2 times, and you ask him that your geometric multiplicity means how many eigenvectors will you give. He says that it will be less than or equal to algebraic multiplicity, and which is equal to 2. Therefore you have two cases. Two cases are geometric multiplicity is 2 or geometric multiplicity is 3. Sorry, geometric multiplicity is 1 or geometric multiplicity is 2. Okay, I think this is clear to everyone. Now now what happens is, today is subcase 1. Today is subcase 1 when geometric multiplicity of lambda 2 is 2. What it means that lambda 2 is giving two eigenvectors x2 and x3. As a result, you are able to find this matrix capital P, which is formed by x1, then x2, and then x3. And when you multiply it in the form P inverse AP, it will become diag lambda 1, lambda 2, and lambda 2. I hope this thing is clear to you. Now, subcase 2 is subcase 2 is this eigenvalue lambda 2 itself occurs 2 times, but it gives only one eigenvector. So you have so you have for lambda 2 you have only one eigenvector. Now when you start making this matrix capital P, this capital P is x1 and then x2. We need one more vector which is not available. This means that there, or we cannot make or form this matrix capital P. Thus P does not exist. It means matrix means matrix capital A is not diagonalizable. Matrix capital A is not diagonalizable. So now the thing is when you have a matrix capital A, its all eigenvalues are distinct. If all eigenvalues are distinct, then every eigenvalue will be giving its own eigenvector, and you will be able to find the matrix P, and hence the matrix A will be diagonalizable. So all eigenvalues are distinct implies A is diagonalizable. Now, second case is some eigenvalues repeat. When some eigenvalues repeat, then the matrix can be diagonalizable or it can be not diagonalizable. Now it depends. You see, when you have this case in which you have lambda 1, lambda 2, and lambda 2, lambda 1 do not create any problem. It occurs as eigenvalue once and it gives one eigenvector. The problem, if it exists, will be created by the eigenvalue lambda 2, because it is himself occurring 2 times as eigenvalue, but it is his wish that he will be giving one eigenvector or two eigenvectors. If he gives two eigenvectors means we see we say that geometric multiplicity is less than algebraic multiplicity, is less than or equal to algebraic multiplicity. If geometric multiplicity is equal to algebraic multiplicity, this means that lambda 2 algebraic multiplicity is 2 and geometric multiplicity is also 2. It means that when it occurs two times, it gives as eigenvalue, then it gives two eigenvectors also, then there will not be any shortage of eigenvectors. In this case, when gm is equal to am, then a is diagonalizable. But if gm is less than am, this means that eigenvalues, we have three eigenvalues, but eigenvectors we will not be having three eigenvectors, therefore will not be able to make this matrix P, and hence A is not diagonalizable. Is not diagonalizable. So this is the thing. I hope this is clear to you. We will do some theorems and numericals to make it clear. So I am writing three examples for you. First example is I will not do these. I will just give the hints and you will do the part. So first is 1 1 2 and minus 1 2 1 and 0 1 3. This is your matrix. This is your matrix, and when you find its eigenvalues, you say that the eigenvalues, I have book, I am writing from this, eigenvalues will be 1 2 3, and the eigenvalues obviously are all distinct. All distinct. If the values are all distinct, then you directly know that it will be giving these eigenvalues 1 2 3 and will be giving three eigenvectors, and P will be there and the matrix will be diagonalizable. One question is, they ask you, is it diagonalizable? Second is, diagonalize it. So the thing is, question can appear in two ways. They simply ask, is it diagonalizable? Say yes or no. Second question is, find P for which, find P which makes A diagonalizable. So you have to find eigenvectors, eigenvectors for these eigenvalues, for these eigenvalues. So when you will be having these eigenvectors, then you will be having this matrix, and then you will say that P inverse AP is diagonal, 1 2 3, or you can say 1 0 0 0 2 0 0 0 3. So this is first question. This is first question. You can say this is assignment for you. Please do these numericals, do not ignore them. Next is this is 1 2 3, then 0 4 6, then 0 4 9. This is another numerical. When you will find its eigenvalues, you will find that the eigenvalues for this matrix are 1 1 and 12. 1 1 and 12. Now you will not worry about lambda is equal to 12. You know that it will give one eigenvector. So lambda is equal to 12 will give one eigenvector. When you ask lambda is equal to 1, I can do this. When you ask lambda is equal to 1, it will become a minus lambda I into capital X is equal to 0, implies 0 2 3, 0 3 6, 0 4 8 into capital X is equal to 0. It is clearly understood that the rank is 2. Since the rank is 2, therefore it will be giving only one eigenvector. So you have X, and the solution will be of the form 1 0 0. Okay, solution of this system will be of the form 1 0 0. So you see lambda itself occurs as eigenvalue twice, but it gives only one eigenvector. So you say geometric multiplicity of lambda is equal to 1 is less than algebraic multiplicity of lambda is equal to 1. Therefore we are not able to find 3 eigenvectors, I mean to say that this P matrix is short of one eigenvector. So this P matrix does not exist. So you say therefore P does not exist, and when this P does not exist, you say A is not diagonalizable. So question is this diagonalizable? This matrix capital A, is this diagonalizable? So you find characteristic equation, you find eigenvalues. You will not find eigenvector for lambda is equal to 12. First you will find eigenvector for lambda is equal to 1. When you find eigenvector for lambda is equal to 1, you say that lambda is equal to 1 is giving only one vector. Therefore, even if lambda is equal to 12, give one eigenvector, you will not be able to make this matrix capital P, and hence this capital A cannot be diagonalizable. Now, third example is this is minus 944 minus 834, and this is 16 8 and 7. This is your matrix. So you find eigenvalues. When you find eigenvalues, it becomes lambda is equal to minus 1 and 3. Again, lambda is equal to 3 is occurring only once, therefore it will be giving one eigenvalue, one eigenvector. Not a problem in this. Lambda is equal to 1 can create problem. So you take lambda is equal to minus 1. When you take lambda is equal to minus 1, it becomes a minus whatever a plus I into x is equal to 0, so that it becomes minus 844 minus 1648 88. It becomes into capital X is equal to 0. So you see that it will be minus 211000000. So it is clear that rank is 1, and therefore it will be giving two solutions. I can directly write the solutions. These solutions will be 1 0 and 2x. This is minus 2x plus y plus z. Okay, so this is and then is equal to 0, and this is 0 2. These two will be the solution. So you say that lambda is equal to minus 1 is giving one eigen, lambda is equal to minus 1 is giving two eigenvectors, and lambda is equal to 12, lambda is equal to, question is, okay, lambda is equal to 3 will also give one eigen vector. Therefore capital P will be formed, and hence the matrix is diagonalizable. Now again the question is it diagonalizable or find P? Okay, question can come in two ways. If it comes in the form in which they want you to find the matrix capital P, then you will have to find the eigenvector for lambda is equal to 3 also. Otherwise you say, okay, geometric multiplicity of lambda is equal to minus 1 is equal to algebraic multiplicity of lambda is equal to minus 1, hence the matrix is diagonalizable. Okay, I hope this is clear to everyone, and I request you all to do these three numericals. Next is a theorem. Theorem is, if capital A has all distinct eigenvalues, then capital A will be diagonalizable. So what you say? You say that let capital A be n cross n matrix, and lambda 1, lambda 2, lambda 3 up to so on lambda n be its distinct eigenvalues, with corresponding eigenvectors x1 x2 up to so on xn. So you have n eigenvalues and correspondingly n eigenvectors. Then by definition you know that ax 1 is equal to lambda x1, lambda 1 x1, or I should simply write axi is equal to lambda I xi for all I from 1 to n. For all I from 1 to n. Clear to everyone. Now, the thing is, let capital P, or we should say form capital P is equal to x1, x2, x3 up to so on xn. Okay, form lambda x1, x2 up to so on xn. Okay, now what you say? You say that if I do AP, if I multiply A with P, it will become A into x1, x2 up to so on xn. And how matrix is multiplied? This A will be multiplied with the first column. This A will be multiplied with second column. Up to so on, this A will be multiplied with nth column. Fine. Then you know this thing is lambda 1 x1, this thing is lambda 2 x2 up to so on, this thing is lambda n xn. So you say that this thing will become lambda 1 0 0 up to so on 0, lambda 2 0 0 up to so on 0, 0 0 lambda 3 up to so on 0. Now up to so on, up to so on, up to so on, up to so on, 0 0 0, and then lambda n into sorry into x1 x2 up to so on xn, and this thing is, you know, this thing is P. So what I will say implies AP is equal to diag lambda 1 lambda 2 up to lambda n into P. This P will be pre multiplied with the inverse, and it will become diag lambda 1 lambda 2 up to so on lambda n, and hence therefore or hence you say A is diagonalizable. A is diagonalizable. Now, these things we have done, the things that we have done for matrices. Okay, for matrices we have done this thing. Next is our topic. I mean the article will remain the same, diagonalization, but it will be for linear operators. Okay.